Uh, Hello guys. So in today's session, we are going to model this frame in a space gas environment. Space gas is a famous software on which we can analyze structures and design structures. So the task of today's video is to model this structure, this frame, and analyze it. So first of all, let's look into what kind of um, data that we have. First of all, we have three members, and the boundary condition at support A and D, it is fixed, and for this CD member, the moment of inertia is I. For this BC member, the moment of inertia is 2I. And for this AB member, the moment of inertia is 1.55. So while defining the section, we need to take care of it as well. Then there is this Z loading is being applied. Let's consider it as 19 kilonewton per meter. And there is Z plus 10 kilonewton point load being acted horizontally. So let's consider it as 29 kilonewton. And then there is point load acting at 2 meter. At 2 meter from point B. So it is basically, let's consider it 98 kilonewton acting downward. So this is the whole data that we have for this particular frame. So let's start modeling it. So first of all, in this environment, you need to select this draw member option, or you can use Control D short command. So start drawing, and as we know the length of the member, Control Z, let me do it again. So now I know the length of my first member is 6 meters. So just you can manually enter 6. As you press 6, this box will be appeared. So you can enter your length of the member, 6 meters. And then as you can see, if it is perfectly vertical line, it is green, and if it is perfectly horizontal line, it is red. So as you move, I know the length of my second member is 5 meters. So I enter 5, and then the length of my third member is 3 meters. So I enter 3. So there's the geometry of my frame. So let's zoom fit it. So now this is the geometry. Now I need to define the supports of this system. So first of all, I select node 1, and as I select node 1 and double click on it, I have this property table, and here I can select what kind of support do I need to assign. So let's select this and click OK. The support condition has been assigned. It is not being shown because I have not turned on show node restraint. As I turn on it, as you can see, fixed sign is being appeared, and as you go here and you can see restraint is FFFF. It is showing, which refers to fixed boundary condition. Now double click this node as well and apply fixed boundary condition. Now support has been assigned. Let's define material. So select. Now here you can assign section and you can assign material from this table. As you double click member, this table will be appeared. So now you can import material from the library. As you click on this icon, on this book icon, you can see number of material properties are already being there in the library editor. So here you can select steel. Let's say we are considering our frame is made up of steel. So click OK, apply OK. Now steel properties has been assigned to this member and also to other members as well, because this is the only material property that have been imported. So for all members, steel property has been automatically assigned. As I hover on this member, I can see the member 3 section 1 and material is steel. So now let's define section as well. So again, I go here and I can select any. Now I am selecting the section. So let's select section 89, 254. There's just a random selection. There is no like we are not going to we are just going to analyze the system. So any section we can select, but we need to take care that section should be selected in such a manner that the change of moment of inertia should be incorporated. How we are going to incorporate, we will discuss it in a while. So now as I okay it, now the section has been assigned to each member since there were no section previously. So as we import a section, to all members, the imported section is assigned automatically. Now here I can select wireframe so that the rendering can be removed. So now additionally I will do another thing. I need to define another section of same name or of same properties. I will tell you in a while why am I doing it. Let me do it first. So I know 254, UC 89. So let's again define this section 254, 89. All right, okay. And then again, I'm going to define another section of same properties. Column. Okay. So now I have three sections having same properties obviously, but now since I have three different sections, now I can manipulate their moment of inertia because I need three different sections having three different moment of inertia. So I go there under structure, I have this section properties, select data sheet. As you select it, you have this table. So here in this table, there is the value of moment of inertia. There is the maximum moment of inertia and there is the minimum moment of inertia, or the moment of inertia along weak axis and along stronger axis. So we need to manipulate moment of inertia along a stronger axis. So here for the first member it is 1.5 times of I, for the second member it is 2I, and for the third member it is I. So third member is the value that we could consider as base, and on the basis of this value, these values are computed, right? So let's take this third section as the base value. For the second section, or for the section for the second member, it is 2I. So let's compute that how much this is if I multiply it by 2. So let me calculate multiply by 2. This is the value. So this is the value, or 142,700,000 multiplied by 2, and it is 285.4 e to the power 6. Right. If I am doing it correctly, let me check it again so that I should not have any error in my computation. I'm doing it manually as well. So now this is the value and this is the right. It's good to go. So now for the first member it is, as we have this 1.5 times of I. So now select this value, Control C, go to the calculator, paste it, multiply by 1.5. It is 214 and the other digits are 1.5. It is 214.05 10 raised to power 6. 214.05 10 raised to power 6. This is the value. And let me check it once again so that there should not have any error. There is no error. So the values of moment of inertia have been modified. Click OK. Now go to section member 1 and select section 1 and click OK. Go to member 2 and select section 2 and click OK. Go to member 3 and select member section 3 and click OK. So now you have defined the geometry, you have defined the boundary condition or the supports, and you have defined the materials, and you have defined the section. Now I need to apply loading. So select this member. As you select the member, here now you can apply loading. So first of all, let me apply distributed load and enter 1 here, because this is the first load case that we are going to create. And the value of it will be do observe one thing, that the sign convention is towards the right x-axis positive, to upwards y-axis is positive, and out of the plane z-axis is positive. So now the value of this z, as we assumed before, that it is 19 kilonewton per meter. So let's consider 19, and it is uniformly distributed load, so it should be 19 again. If we change it, then it will not be uniformly distributed, it is varying distributed. So let's take it 19 for, as it is required in this case. So click OK. OK again. Title. Let's enter 1 for a while. And here we have this load case. And if I need to show the value, show diagram annotation. Here I can see it is 19 kilonewton per meter. Now I need to apply load at the end of this member. So again, select this member, go to member concentrated loads. So here you can select the position. I am going to apply the load at the end of the member. So it should be 6 meters, or we can apply in terms of percentage. I do not want to make it complicated, so I'm just selecting under the units actual, and I need to apply the load at the end of the member, which is 6 meters. The member length is 6 meters. So now the force will be in the positive x direction. So it is 29 kilonewton. So here you can see there is 29 kilonewton. Load is being applied at the end of this member. Now select member 2 and go to member concentrated load, since we need to apply this load, which is at 2 meters from point B, and the value of this load is, let's consider 98 kilonewton. Click OK. Here and under units, select actual, select 2 meters, and it is under the loading will be in y direction, and it is negative y, because the load is being applied downward in the y direction. So the load is minus 98. Does that apply? Okay. Here is the loading. The loading has been applied. So now I have done everything. What I need to do at the end, I just need to analyze it. So need linear static analysis. Load case 1. Okay. The analysis has been completed. Let's see what kind of values do we have. So we have these values, or let's turn off loading. So here we have values 100 kilonewton meter, minus 100, and then there's minus 22.54, minus 101, and 117.95 kilonewton. There is the bending moment diagram, and if I select this shear force, there is the shear force diagram, and if I select axial force, this is the axial force diagram. If I need to know the reactions, then I can select show reactions, and here I have the reaction. It is not clear. I can rotate it to make it clear. Since still the visibility of the reaction, since there are number of reactions, so the visibility is not clear. So instead what I can do, I can go into output menu, select text report. I can generate report here. So analysis only. Okay. Here I have the results. So analysis, member forces, node reactions. As I select node reaction, here I have the reaction. Minus 69.9 in X at node 1, and node 1 is our this support. Node 4 is our this support. So here I have in X direction what is the reaction, in Y direction what is the reaction, and in Z direction what is the movement. Similarly, at support or at node 4, which is this support. And if I need to know the member forces here for member 1 at the start of the node and at the end of the node, what are the axial forces, shear forces, and bending moment. Similarly for member 2 and member 3. If I need to know the node displacement, here I have the nodal displacement. I can see the deformed diagram as well. If I check this show displacement, I can see the displacement. Here you can see there's 7.2 mm displacement horizontally, as you can see here, and vertically there is at this node there is 0.11 mm displacement, right? So this is the displacement diagram. So this is all about for today. As you can see, we have modeled this structure and analyzed it in SpaceGass environment, right? So we will do another example in some another video. Till then, goodbye.